Okay, question number 4, and this question is for 16 marks. So I have taken 16 minutes to solve this. Let us see. Right. Elastic climbing rope is adjusted by fixing one end of the rope to the top of a crane. The other end of the rope is connected to a block which is initially at position A. Okay, so you have a block here, and then it is initially at position A. The mass of the rope is negligible. There is no mass. Unextended length of the rope is 60 meters. Unextended length of the rope. So what you do is you just drop it over here from the top here. So as a result of it, the moment you drop it comes down, and from position A to B the block falls freely. Okay, at position B the rope starts to extend because it's an elastic rope. It will start extending and will reach the point C. Calculate the position of the block at position B. So what is the velocity at this point? So how do we do? Simple. mgh, okay, is equal to half mv square, right? Where what is the height? Height is this height. Okay, whatever was the height of this block here, from here to here it has come, so this should be equal to half mv square. So this m and m goes away, so you have v square is equal to 2gh. And now what we do is we'll calculate this. We'll put 2 into 9.8 multiplied by what is the height? Height is going to be 60 meters. 60 meters. So let us use my calculator to find out what is this value. So this should be 2 into 9.8 multiplied by 60, which will be equal to 1176. And let me take the square root of this. So this gives out to be around 34.3. Okay, so this you can write v is equal to square root of this, which should be 34.3 meter per second. That was the velocity of the block at point B. At position C, the speed of the block reaches 0 at position C at this point, because it has to keep on extending. So as it starts extending, there is a restoring force acting upwards. So the velocity of the block definitely has to reduce as it comes, and when it reaches this point, velocity becomes 0. Okay, maximum extension. Then now let us read what is happening. Time taken for the block to fall from B to C is 0.759 seconds. Time taken to fall from here to here is 0.759 seconds. Okay, and then what's the next thing? The mass of the block is given. Determine the magnitude of the average resultant force acting on the block between B and C. Average resultant force. Do not use V minus U divided by 2U over here. Okay, so what we do is, now we know that M into delta V, if you take, okay, M into delta V is now, what is M here? M is already given to you. What is the value? M is 80 kg multiplied by, what is V minus U? So I said do use, not do not use. Do use. So V minus U. What is U here? U here is the velocity at this point. What was this value? We calculated in the earlier problem. 34.3. 34.3. And this is your V here. This is your V here. V becomes 0 here. So therefore, if I do that, this will become V minus U, which will be 0 minus U. Use 34.3. We write down 34.3 should now be equal to F times delta T. Okay, impulse. So therefore, your average force F should be equal to 80 into 34.3 divided by delta T. What is delta T? Delta T is nothing but 0.759 seconds. 0.759 seconds. Of course, there is a negative sign here. I'll put the negative. But you see here, it is asked about the magnitude of the average. So therefore, negative sign is not required. Okay, now let us calculate what is this value. This value comes out to be 80 into 34.3 divided by 0.759, which will be 3615. 3615 meter. Is it meter? No, it is force here, right? So this should be Newton over here. Okay, now let us move on to the next question. Sketch on the diagram the average resultant force acting on the block between point B and C. Okay, so definitely it is not B, because there is a tension also here. See, what is B and C? See, this is your point C here. This is your point C here. Between B and C, it means what? This is your point B. The block is still at this point. Okay, it has not completely reached over here. Okay, so if it has completely reached and it is at the equilibrium, then you can say tension is equal to FB over here. So as a result of it, this will be your force over here. This length of this force will be larger over here. Okay, this will be larger than compared to this. So what you do is you need to draw a line a little bit bigger. Okay, and then you have to write the value of F over here. Okay, now what is this? Okay, so there are 2 marks for this. The first one is goes you for the length of the force. Second one is indicate the upward arrow. Okay, so this will give you the 2 marks, right? Then calculate the magnitude of the average force exerted by the rope on the block between the points B and C. So therefore, what is the net force is asking. So if I draw the free body diagram for this one here, I can now write F minus mg is equal to ma. What is this ma? Ma you already found out, which is nothing but the net force. So I can now write F is equal to mg plus F net. This is what we have. So therefore, now F net is already known to you. What is F net? We already found out. Not F net, sorry. This is your F average. F average. We already found out F average. Where is it? We calculated here 3615, right? So therefore, now I just need to add mg over this. F should be equal to mg plus 3615. What is m? Mass of the object. Where is the mass of the object? Mass of the object was given as 80. So I will just write this as 80 multiplied by 9.8 plus 3615. When I do this, what is the answer I get? So it should be 3615 plus I don't think, I'll just cancel this. I'll write this 80 into 9.8 comes out to be around 784. 784 plus 3615 comes out to be around 4,399. 4,399 closely, this is equal to 4400 Newton. That's the right answer. Okay, now let us move on to the next one. For the rope and block, describe the energy changes that takes place between A and B. Between A and B. Where is A here? A is somewhere over here. A is here, and you drop the block from here. Here in this region, there was a free fall. Okay, there was no elasticity coming into play. So therefore, what is the kind of energy here? The energy transformation that takes place here is you had a potential energy and you had a kinetic energy here, right? So potential energy got converted into kinetic energy. Or the best way to write is, you should write loss of potential energy is equal to gain in kinetic energy of the block. This is the right way to write. Okay. Between B and C. Between B and C. What's happening between B and C? So here this had a maximum velocity. But when it started going downwards, once again, because it did not stop here, started going downwards, what happened? The velocity started to reduce over here. Okay, you had a velocity, but this was lesser than this one, which means what? When the velocity is reducing, that means it is losing some kinetic energy also. So it is losing potential energy, it is also losing kinetic energy, but what is increasing? The elastic energy is increasing over here, right? So we should now write here between B and C as loss of both potential energy and kinetic energy is equal to gain in elastic potential energy, EPE. You can write so much over here. Then next one, the length reached by the rope at C is 77.4 meter. Suggests how energy conservations could be used to determine the elastic constant of the rope. Okay, we need to find out elastic constant, spring constant we need to find. Okay, so now let us write down briefly this diagram. This is your point A, this was your point B. In this region there was only free fall. Okay, and this again came back to the point C, and this length is already given to you as 77.4 meter. Now you want to find out the spring constant of this one. Now how do you find? Conservation of energy is the only way. Okay, now how do you find conservation of energy here? You will apply something like half kx square. What is this? The energy gained at this point C should now be equal to, take up this one here. This should be equal to mgh. What is this h? This is your h plus half mvb square. That's half mvb square. Okay, whatever is the velocity, all the velocity, whatever the kinetic energy it has, entire kinetic energy is now given to this block. Okay, along with this one. So as a result of this, okay, this has got converted to so much. So thus this is your, this equation can be used over here. Okay, or there is one more way to do it. What is that way? That way is that you can say whatever is the energy at this point, the energy at this point is equal to energy at this point C. You can mention this also. Okay, but anyway, this is more convenient, so we are not going to use this one here. This would be the right answer. Right. Next, in another test, the block hangs in equilibrium at the end of the same elastic rope. Another test. Okay, so this is your test. Now this is the block over here. The elastic constant of the rope is 400, and the block is pulled 3.5 meters below, vertically below the equilibrium position. It is then released from this. So this is the point. You release it, you pull it downwards by additional distance, and the distance between these two is seen to be 3.5 meters. Calculate the time taken for the block to return to the equilibrium position for the first time. What is the time taken by the block? The moment you release it, the block immediately springs backwards, right? It goes backwards like this and it reaches this point. Now, what is the time taken by it to reach this point? This is what is the question. Now, since the value of k is given, see, when you release it, what will happen? This block will go here, then it will not stop here. It will once again go here, and then once again it will come back here, then it will come back over here. What will happen here? This will now produce an SHM, right? What is the time period of an SHM here? This is given by 2 pi into root of m by k. Okay. Now, what all is given to us now? Is t given to you? No, t is not given to you. You need to find out this. Okay. And this is 2 pi into square root of, what is m here? Is the mass of the block given? Let us find out what is the mass of the block given. Elastic constant is given. I need the value of the m here. M. What is the value of m? Is it given? M was given to be 80 kg. That's already given. Okay. See, are we using the same block? See, in other terms, the block hangs in equilibrium by the end of the same elastic rope. The elastic rope constant of the rope is given. Block is pulled. So this is the same mass. 80 divided by k is 400. 400. This goes away here. 8 ones are 8 5s are. This should be equal to 2 pi by root 5 seconds. This is the time period. Now, is this the time taken by the block to go here? No, that is not the time. See, it takes a time t here to start from here to go here. It once again takes the same time t here to compress it. Once again comes back at the same time. Once again comes to compress at the same time. Which means this time from here to here is nothing but t by 4 seconds. So thus you divide this by 4. So therefore your t is equal to t by 4, which should be 2 pi by root 5 divided by 4, which should now be written as 2 1s are, 2 2s are, 2 2s are, it should be 5 by 2 root 5. Let us calculate what is that value. So this should now be 5 by 2 root 5. 2. Okay, first let us find out the value of root 5. I'll get the value of 5 here, square root of 5 over here, multiply this by 2. I get the answer of 4.47. Take the reciprocal of this, multiply this by 3.14. So this gives you 0.7 seconds. 0.7 seconds over here. Thus the time taken here is 0.7 seconds. So this is your right answer. Right. Okay. And then next, calculate the speed of the block as it passes through the equilibrium position. Okay. At the equilibrium position, what will happen? The speed is seen to be maximum. So what is this formula here? This should be A times omega. What is A? Amplitude. What is omega? 2 pi divided by t. Do I know all these parameters? Definitely we know. What is A? Now let us see here. A here, see, this was your equilibrium position. From here it has been pulled downwards. So this value is nothing but A, right? So the value of A is seen to be 3.5 multiplied by 2 pi. 2 pi divided by capital T. What is capital T? Capital T we have found out here, which is nothing but 2 pi by root 5, right? So let us find out. Let us write down this as 2 pi divided by root 5. 2 pi goes away. So you get the answer as 3.5 times root 5. So let us find out what is this V max. Calculate this. So this should now be, once again I'll find the value of 5. Root 5, I will find this value. Multiply this by 3.5. I get the answer 7.83. I get the answer 7.83 meter per second. Okay. This is the maximum speed of the object when it goes upwards at the equilibrium position. Right. Let me find out whether my answers are right. That's correct. Okay. So with this we come to an end to this particular problem. We will see tomorrow with one more problem. Thank you. So before you leave, do like, share and subscribe to my channel for more such updates. Thank you.